Hi everyone. Today we'll understand the connection between differentiability of a function and continuity of a function. If you would like to try the next exercise on your own first, download these notes using the link in the video description. We must determine which of the following functions are differentiable and which are not. If you are not sure what the word differentiable means, or if you are not sure how to determine if a function is differentiable by looking at its graph, I will add a link in the video description leading you to a video in which I explain how to check if a given function is differentiable by looking at its graph, and I explain what the word differentiable means. I believe that the first function is differentiable. It is a straight line. The second one is not differentiable. It has a cusp. Third one is not differentiable. It has a jump. Fourth one is differentiable. It is a smooth function. Fifth one is not differentiable. It has a hole. Sixth one is differentiable. It's a smooth function. Seventh one, not differentiable. It has a corner. Eighth one, differentiable. It is a smooth function. Take a look at the functions in green circles. They all have one feature. They share one feature. That feature is they are all continuous. I can draw all of them without lifting up my pencil. This means and suggests that if a function is differentiable, it's always continuous. Let's take a look at the red circles. There are some examples there that suggest that if a function is not continuous, then it cannot be differentiable. Notice that all the examples of discontinuous functions, which was this one and this one, were not differentiable. Mathematicians proved that this is a rule. If a function is differentiable, if the derivative exists, then the function is continuous. On the other hand, if the function is not continuous, then it cannot be differentiable. Just like in the examples above, these two examples were not continuous, they couldn't be differentiable. And the differentiable examples were all continuous. Let's see if we understand this theorem by completing the next problem. If you would like to try it on your own first, stop the video now. We must say if these sentences are true or false. Let's give it a try. The first one says that differentiable functions are always continuous. Is that true? I believe it's true. It is the first statement, the first sentence of the first theorem. If a function is differentiable, then it is continuous. The first one is true. Now, are continuous functions always differentiable? I believe that is not true. If you take a look at some examples above, we had a continuous function that was not differentiable. So just because a function is continuous doesn't mean it has to be differentiable. The second statement is false. If the derivative at 3 exists, does it mean that f is continuous at 3? I believe the answer is yes. If the derivative exists, that means that the function is differentiable there, and we know that differentiable means continuous. So this sentence is true. What about part D? If the function is continuous at 3, then the derivative at 3 must exist. I believe this is false. Just because the function is continuous does not mean that the derivative must exist. It can, but it doesn't have to. So I will say this is false. If f of 3 exists, does it mean that f prime of 3 exists? Let's think. If the value of the function exists, does it tell us anything about the derivative? I don't think so. Take a look at this example. The value of the function existed here, but the function was not differentiable there. So this statement is not true. Just because the value of the function exists doesn't mean that the derivative must exist. Let's take a look at the next one. If the derivative at 3 exists, then the value of the function must exist. If the derivative exists, that means that the function is differentiable there. According to this theorem, being differentiable means it is continuous. So I definitely know that the function is continuous at 3. And because it's continuous, it cannot have a hole. It must exist there. So f of 3 must exist. To see if we understand this theorem even better, I have one more exercise for us. If you would like to try this problem on your own first, stop the video now. We must draw functions. First, that is continuous differentiable, then not continuous and not differentiable, then continuous but not differentiable, and then differentiable but not continuous. Let's do it step by step. First, I need a function that is both continuous and differentiable. Let me try. I believe a line would work well. We know that a straight line is continuous, and we know that it is differentiable. Its derivative is its slope. Now I need a function that is not continuous and not differentiable. I believe a function with a hole would work. If a function has a hole, it's not continuous, and because it has a hole, it cannot be differentiable there either. What about a function that is continuous but not differentiable? I must draw it without lifting up my pencil, but I must have a place where this function doesn't have a derivative. I think the easiest way to do it is to draw a function with a corner. This function is continuous, but it is not differentiable at the corner. Finally, I need to draw a function that is differentiable but not continuous. And I believe this is not possible, because we just said that any differentiable function is continuous. There is no way to draw a function that is differentiable but is not continuous.